Overengineering sounds like a virtue. It suggests strength, durability, and a margin of safety so large that failure becomes almost impossible. Many people assume that if a little reinforcement is good, then doubling it must be better. But in modern engineering, that logic often fails. Beyond a certain point, adding more strength, more backup, or more capacity does not make a system better. It can make it heavier, harder to maintain, more expensive to run, and in some cases even less reliable. In this video, we'll examine what overengineering looks like in practice, how it creates hidden costs, and why good engineering is usually about the right margin, not the biggest one. To understand this, we first need a technical definition. Overengineering happens when a system is given substantially more performance capability, structural capacity, or safety margin than its actual operating conditions and risk model require. Engineering always includes margin. Bridges, aircraft structures, and pressure vessels are not designed to sit right at the edge of failure. But when margins grow without a proportional justification in risk, they stop being protective and start becoming costly. And those costs are not limited to money. Every added layer of capacity affects the rest of the system in ways engineers then have to manage. At the mechanism level, one of the most common effects of overengineering is added mass. Additional material, thicker housings, or higher capacity components all make a system heavier. Weight increases inertia. Inertia increases required force for acceleration, according to Newton's second law, where force equals mass times acceleration. In dynamic systems such as vehicles or rotating machinery, increased mass translates directly into higher energy consumption. Even in static systems, heavier structures impose higher loads on foundations and support members, triggering further structural reinforcement. Imagine an automotive suspension component designed for a peak load of 20 kilonewtons. If its capacity is increased to 40 kilonewtons without any real change in operating conditions, the thicker component increases unsprung mass by several kilograms. That increase in unsprung mass matters because it affects ride quality, wheel control, and tire contact with the road. A heavier component may then require stiffer springs and stronger dampers to control motion properly. The result is increased cost, increased material usage, and potentially reduced ride comfort. Overengineering also affects manufacturing tolerances. Higher capacity components often require tighter machining tolerances or more advanced materials. These processes increase machining time, tooling wear, and inspection requirements. For example, designing a gearbox rated for double the required torque may necessitate thicker gear teeth, different heat treatment, and higher grade alloys. Each improvement increases cost per unit, but unless the operating torque justifies the upgrade, the additional capability remains unused. Energy systems reveal the same pattern. In electrical engineering, oversizing transformers or conductors can reduce losses, but only up to a point that makes economic sense. The power lost in a conductor depends on current and resistance, often expressed as I squared R. So lowering resistance by increasing conductor size can reduce wasted heat. But if the system operates at partial load most of the time, then the savings from extra copper may never repay the added cost. In that case, the design is no longer optimized. It is simply carrying more material and capital than the operating profile justifies. Another hidden cost of overengineering is complexity. This often happens when engineers add subsystems in the name of reliability. Redundant sensors, backup actuators, interlocks, and fail-safe logic can be essential in the right application. In aviation or nuclear engineering, they may be absolutely necessary, but every added component also has its own failure probability, its own maintenance burden, and its own interface with the rest of the system. So the design challenge shifts. Instead of optimizing the core function, engineers now have to manage the reliability of a more complicated architecture. To quantify this, consider a simplified reliability model. Imagine a system with 5 critical components connected in series, each with a reliability of 0.98. The overall reliability is not 0.98. It is 0.98 raised to the 5th power, which is about 0.903. In other words, the whole system is less reliable than any one of its parts, because every required element must work. Maintenance implications are often overlooked too. Larger, heavier, and more complex systems require longer inspection intervals and more specialized tooling. For example, overspecified industrial pumps with higher pressure housings may demand more robust sealing systems. These seals operate under greater compression and may require more frequent replacement. Downtime increases. Spare parts inventory increases. Hence, the operational expense accumulates over years of service. There are legitimate contexts where extreme conservatism is justified. Nuclear containment structures, offshore drilling platforms, and crewed spacecraft require substantial safety margins due to catastrophic failure consequences. However, these margins are derived from rigorous probabilistic risk assessment and defined hazard models. They are not arbitrary multipliers. Overengineering becomes problematic when margins expand without data-driven justification. In such cases, the system departs from optimized design space and enters diminishing returns territory. Another hidden cost is environmental. Additional material means additional extraction, processing, and transportation. Steel, aluminum, and composite manufacturing carry embodied energy. If a component uses 30% more material than required, lifecycle emissions increase proportionally. In infrastructure projects, these differences scale dramatically. Overengineering at national scale translates into higher resource consumption. Modern engineering practice increasingly incorporates lifecycle assessment to prevent unnecessary over-design. Human factors also play a role. Complex, overbuilt systems can be harder to understand and operate. In control systems, excessive interlocks and layered safety logic may overwhelm operators during abnormal events. The 3 Mile Island incident in 1979 is often cited as a reminder that complexity and ambiguous information can interfere with human decision-making during abnormal events. While not solely caused by overengineering, the lesson is clear. Additional systems must improve clarity, not obscure it. Boundary conditions must be acknowledged as well. Engineers rarely know exact future loads. Uncertainty in material properties, environmental conditions, and user behavior justifies safety factors. Standards bodies such as ASME and IEEE provide recommended margins precisely to account for uncertainty. The challenge is distinguishing between prudent margin and reflexive over-design. Advanced modeling, finite element analysis, and real-world load monitoring now allow tighter calibration of safety factors than in previous decades. At its core, engineering is the management of trade-offs under constraint. Strength competes with weight. Redundancy competes with complexity. Performance competes with cost. When one variable is maximized, without considering system-level consequences, the design drifts from optimality. Overengineering is rarely dramatic. It appears as incremental decisions, each seemingly reasonable. Only when aggregated do these decisions reveal cumulative cost. The practical implication for engineers is to quantify margins explicitly. Define expected load. Define worst-case credible load. Apply an appropriate factor of safety derived from standards and empirical data. Then test sensitivity. What happens if the factor increases by 20%? Does system weight increase by 10%? Does cost increase by 15%? These calculations transform design from intuition-driven conservatism into data-driven optimization. In synthesis, overengineering is not about strength being bad. It is about imbalance. Excess capacity consumes material, energy, capital, and cognitive bandwidth. In dynamic systems, it can degrade performance. In complex systems, it can reduce reliability. In large-scale infrastructure, it can amplify environmental impact. Good engineering aims for sufficiency with margin, not maximalism without analysis. If this analysis clarified how modern engineering systems balance safety, cost, and performance, consider subscribing to Engineering Manual for more technical explorations.